This could be a monumental breakthrough. Scientists, leveraging NASA's James Webb Space Telescope, have made a groundbreaking discovery. The supernova, designated Hope, is more than just another cosmic explosion. It offers researchers a powerful new tool for measuring the universe's expansion rate, the Hubble constant. Even more excitingly, this finding could help resolve a long-standing debate in cosmology, the so-called Hubble tension. So why is supernova hope so important? And how does it aid in our understanding of cosmic expansion? In this video, we will explore the discovery of supernova hope and answer these questions. Supernova hope is a specific type of supernova that was observed through a phenomenon known as gravitational lensing. Gravitational lensing occurs when a massive object, such as a galaxy cluster, bends the light from a much more distant object, thereby forming multiple images at the distant object's location. In this particular case, the galaxy cluster PLCKG 287, located 3.6 billion light-years away, acted as a lens, splitting the light from a remote supernova in a background galaxy into 3 distinct images. This effect is invaluable to astronomers because it enables them to observe objects that would otherwise be too faint or too far away for detailed study. But the reason supernova hope is a major finding is that it is a type Ia supernova, an exploding star with a predictable brightness. This type of supernova is often referred to as a standard candle because of their known intrinsic luminosity. Astronomers can utilize them to measure distances in the cosmos, making them a key tool for understanding the universe's expansion speed. Now you might be wondering, how did astronomers uncover this supernova? In 2015, the Hubble Space Telescope imaged the same galaxy cluster, but the supernova was not there. Let's fast forward to 2023, when the Webb Space Telescope imaged the cluster during observation time for the Ionization and Lensing Science program. The team noticed 3 specks of light that were absent in the Hubble images and immediately suspected they had found a new stellar event. When the Webb data arrived, the team, led by Brandifar at the University of Arizona, quickly analyzed the images. They excitedly confirmed that these specks of light were indeed a supernova exploding in a galaxy far more distant than the cluster acting as the lens. The galaxy cluster's gravitational lensing had split the supernova's light into 3 images. This is like seeing the very same star explode at 3 different moments in time. Thus, supernova hope was unveiled. The significance of type Ia supernovae as standard candles. Type Ia supernovae are extremely reliable tools for measuring cosmic expansion due to their predictability. This predictability stems from the explosion process itself. This type of supernova occurs when a white dwarf, the remnant of a smaller star that has exhausted its nuclear fuel, accrues material from a companion star. Once it reaches a critical mass, the white dwarf undergoes a thermonuclear explosion, releasing a consistent amount of energy. Supernova hope perfectly fits this model. Astronomers can accurately determine its distance by measuring how much its light has dimmed on its journey to Earth. This leads us to the Hubble constant, a key parameter in cosmology that describes the rate of the universe's expansion. To measure it, astronomers require 2 pieces of information: the distance to the receding galaxies and their recession velocity. This type of supernova provides the distance, while redshift, the stretching of light due to cosmic expansion, reveals the velocity. This brings forth the Hubble tension, a discrepancy between different measurements of the Hubble constant. Local measurements, including those using Cepheids and supernovae, tend to yield a value of approximately 73 kilometers per second per megaparsecs. However, observations of the early universe, such as the cosmic microwave background, CMB, measured by the Planck satellite, indicate a lower value, approximately 67 kilometers per second per megaparsec. This gap between the local and early universe measurements has been one of the greatest enigmas in cosmology. The impact of the Hubble tension. The SHOES project, led by Adam Rees, has been at the forefront of measuring the Hubble constant using type Ia supernovae. This project has been vital in highlighting the Hubble tension and consistently finds a higher value for the Hubble constant. Supernova Hope, through gravitational lensing, offers an independent method to measure the expansion rate. But Supernova Hope is not the first lens supernova to contribute to this discussion. The Hubble Space Telescope observed another gravitationally lensed type Ia supernova, PTF6GU, which also offered a new way to measure the Hubble constant. Similarly, SN-REF-STAL was the first supernova to be observed with multiple gravitational lensing images, allowing astronomers to study time delays and refine their measurement of the cosmic expansion rate. However, Supernova Hope excels due to the precision of its measurement, thanks to the advanced instrumentation of the James Webb Space Telescope. It permits the observation of lensed supernovae with unprecedented accuracy, helping to refine our comprehension of the Hubble constant. The initial measurement for Supernova Hope is 75.4 kilometers per second per megaparsec, still indicating some tension with the value derived from the early universe, bringing us closer to resolving this long-standing puzzle. Now let's delve into some of the theoretical models proposed to resolve the Hubble tension. One prominent theory that could potentially resolve the Hubble tension involves self-interacting dark matter, SIDM. In this model, dark matter particles are able to interact with each other, unlike the conventional model, where dark matter is assumed to interact only through gravity. These self-interactions could affect the formation of structures in the early universe and potentially influence the measurements of cosmic expansion. Additionally, evolving dark energy, the mysterious force driving the universe's accelerating expansion, might play a role. Dark energy, whose behavior changes over time, could help explain the disparity in the Hubble constant measured in the local and early universe. Another possible explanation for the Hubble tension lies in modified gravity theories. One such theory is modified Newtonian dynamics, MOND. It suggests that gravity behaves differently on cosmic scales than predicted by general relativity. In MOND, the laws of gravity may need adjustment when applied to the vast distances between galaxies. This modification might reconcile the difference between local measurements of the Hubble constant and those based on observations of the cosmic microwave background, CMB, from the early universe. The underlying idea of modified gravity theories is that our current understanding of gravity may need revision, especially when applied to the grand scales of the cosmos. If these theories hold true, they might offer an alternative explanation for the Hubble tension without requiring dark energy or dark matter as the primary factors. Thanks for watching. Feel free to leave comments to discuss.